first, a short overview about my presentation. I will give you in the beginning a definition of my efficiency. Then I will discuss some relevant parameters and possible maximization of these parameters. Afterwards, I will give you a theoretical description of the motion of the car. For this, I need some determination of important parameters. At the end, I will compare my theory and my experiments. So, our definition of efficiency. We define here the problem-specific efficiency as the distance traveled by a specific amount of energy. This is very similar to the definition of efficiency by normal cars. There we have the cruising range per fuel tank. So if we consider now constant starting energy under constant environmental conditions, we have always a given amount of energy at the beginning of the movement. So what we have done is to optimize the distance traveled for a specific amount of energy, because this will also maximize the efficiency of the car. So to the relevant parameters. We have two friction forces. The rolling friction of the wheels here and the air resistance. Actually, these are the two forces which decelerates the car. Then we can vary the shape of the exhaust port, which will vary the airflow out of the volume of the balloon. When we vary the air volume in the balloon, we will also vary the efficiency, because we vary the starting energy of the car. For a reduction of our air resistance, we can also vary our shape of the car. So, some possibilities of optimization of these parameters. For the reduction of friction, we can first reduce the air resistance, as I said, with the shape of the car. Here it's important to have a small cross-section of the car and a small CD value. Then we should reduce the rolling friction. We can do this by a reduction of the mass, and we can use oil as a lubricant. At the end, we use a plastic tube for our nozzle, because this tube material has a very small roughness, and therefore we have a very small pressure loss at the nozzle. In our nozzle we have airflow, and to compute this airflow we need to know if we have a turbulent or a laminar flow. For this we calculate the Reynolds number, which is given by this formula here. We have the characteristic length of the tube, which is 2 times the radius, so the diameter. In our case the radius was 3.5 millimeters. We made a measurement here, where we measured the volume in dependence of the time. We simply let the air go out. So we get this black measurement points, and with the red linear regression. Out of this we can easily compute the velocity of the expelled air and get a value of about 75 meters per second. Therefore we can compute our Reynolds number, which is about 40,000, and normally when you have a Reynolds number greater than 2,000 in a tube, you will have a turbulent flow. So now we can compute the velocity of the expelled air. First, to the propulsion force. Due to Newton's axiom, it's the derivative of the momentum here, which can also be written in this form here. When we make some energy considerations for the airflow, we get this formula here, but we have to introduce a factor, which you can see here, which is derived from the Darcy-Weisbach equation, because in our tube we have some energy losses to the roughness, due to the roughness of the side walls. So in this factor we have another factor, which is called the Darcy factor F, and we can read it out of the empirical Moody chart. And for our nozzle we get a value of about 0.02. So now to the theoretical motion of the car. If we consider now one-dimensional movement and the propulsion force to be greater than the friction forces, the equation of movement will be as follows. We have here the acceleration force on the left side, which is the propulsion force minus the friction forces. So for the propulsion force we can write this formula, which we have derived before. Then we have the rolling friction and the air friction here. We use Newton friction. A very interesting parameter here in this formula is the radius of the nozzle. We have, because it's not clear if we have a very big radius, if we travel also a big distance and have a big efficiency. So to determine our efficiency of the car, we need to know our initial starting energy. To do this, we take the action integral over the force out of the nozzle, which you can see here. Then we take our definition of the pressure and combine these two equations to another one here. And with some differential substitutions, we end in this equation for our initial energy in the balloon. Here in this video, you can see the balloon we used. It's a very long balloon. This has several advantages. First, you have a small cross-section, which leads to a small air resistance. And second, you have a comparatively high air pressure in it, because you have a big ratio between the surface of the balloon and the volume in it. Out of this video, we have done some video analysis, which you can see here, a picture out of it. And we assumed the balloon as a rotational corpus, and so we could integrate along the cross here to get the volume. Out of this experiment, we have also gained our experimental data for the first graph I've shown you. For our velocity and our initial energy in the balloon, we needed the pressure curve independent on the time. So here you see the balloon, our experimental setup. Here the air goes out into the pneumatic tank, and we can read up the volume here, and at the same time we can measure the pressure with the sensor attached. The experiment is done stepwise. So actually we measure here the pressure independence on the volume, but as we know the volume independence on the time, we can take the inverse function, and with this relation we get also the pressure independence on the time. So the influence of the wear. This will have an influence because the pressure curve looks not equal after each blowing up and leaving extruded. The first time the pressure curve is higher, and then after several times it will be lower. And when you consider 10 times or more letting the balloon extruded, the pressure curve can be considered as equal, as you see here for the last curves. For our theory, we need to determine the rolling friction factor, and we have done this on an inclined plane. We have put the car on the plane and let it rolling down and measure the current elongation with a laser rangefinder. And we get this curve here, and with a quadratic regression, we get our acceleration here, and out of this formula, we can compute our rolling friction factor, which is about 0.021. For the determination of our air resistance, we need the CD value and the cross-section of the car. But as we need only the product of these, we can measure them in one experiment. You see here a wind tunnel where the air goes in this direction and pushes the car in this direction. So we can measure the force which is on the car with this force sensor here. Out of this compute the CD value times the cross-section of the car. We get a value of about 34 centimeters squared. So now to a comparison between theory and experiment. You see here in this graph the same measurement points as before, but the red curve is no regression. It's the theory curve, and is computed out of this formula I give you before the formula for the expelled air. So you see that they fit very well together. The mass will have also a big influence here, because our wear tear weight of the car was 120 grams, and when we change this weight only a very bit, this will have a big influence on the distance. When we add a mass of 25 grams more, our distance will lower of about 4 meters, and this is a very big difference here. We have done this measurement with our car, and we put additional masses on it. Now to the influence of the radius. As I said, this is a very interesting parameter. You see here the distance traveled in dependence on the radius of the nozzle. There's a critical radius of about 1.1 millimeters, where the propulsion force equals the friction forces. For a higher radius, the distance will increase very fast until it reaches a limit for very high radius. And this is theoretically, and as you can see, it is also practically proved by experiment. So here you can see a video of my final car. Now the air goes out of the balloon, the car accelerates, now the air is completely out of the balloon, but because of inertia the car moves forward, and now, because there are friction forces, as I mentioned, the car decelerates and stops. Now, yeah. And to come to my conclusion, here you see one time more my car I used, my final car, and here we have the CDs as wheels, because they have a very small rolling friction factor, they have a small moment of inertia, and a very small cross section, which leads to a small air resistance. Then we use this long balloon here, because it has also a small cross section for a small air resistance, and it has a very high energy density in it, because of the high air pressure. Here at the end you see our nozzle, which has a comparatively big radius, so that the, as I mentioned, the distance will reach saturation for high distances. So our final efficiency of the car we reached was about 1.2 meters per joule. Thank you for your attention.
Thank you. Time for questions.
Yes, thank you for your great presentation. So first of all, according to your definition of efficiency, the point which the efficiency is maximized should synchronize with the point where the efficiency is maximized. Is that correct according to your presentation?
Yeah, I have maximized the efficiency, or what do you want?
Yes, but then for the car to travel a longer distance, it should experience a greater maximum velocity, and it means that it will experience a greater air drag and also the rolling friction, so that it experiences a greater energy loss. Don't you think that should be taken into account?
Yeah, I have taken it into account.
Yes. Also, according to your definition, your formulation of rolling friction, it is not proportional to the velocity of the car. However, according to the contact theory of rolling friction, it should be proportional to the velocity. So, don't you think your term for the rolling friction should include a velocity term as well?
Normally, the definition of rolling friction is not proportional to the velocity. It's not dependent on the velocity. But you have the air resistance.
We'll talk about it in the discussion. Then, have you experimented with different nozzle angle? The nozzle angle, the direction of the thrust force acting on the car.
You mean on an inclined plane, the car?
Yeah, this is a horizontal plane, and this is the nozzle angle. Have you?
Okay. Yeah, I've made experiments and also theory, and the drag force will decrease with the cosine of the angle alpha, and so the efficiency will be lower in this case.
Yes, thank you. Then you mentioned about the turbulence, but then don't you think as the nozzle diameter increases, the flow rate through the nozzle will increase as well, so that it will cause a turbulence, so that there will be a certain pick point in your data for the nozzle radius. Don't you think so?
Yeah, for bigger radius, the correction factor from the Darcy-Weisbach equation changes, but we haven't considered as big a radius because it's not practically possible to have a radius of about 1 meter.
Okay, I'm sorry, the time is over.